No? Ça marche pas? Si? Plus près. Comme ça. Ouais, si, c'est rouge le bouton. C'est bon? Okay. So, it's my pleasure today to welcome Gianfranco Bertone, who is well known to us because he did his PhD here, and he was also for some time a researcher at CNRS. But today he works as a professor of theoretical astroparticle physics at the Faculty of Science at the University of Amsterdam. He works at the GRAPPA Center of Excellence in Gravitation and Astroparticle Physics, for which he acted as a spokesperson until 2019. He's today, he's today also the founding director of the European Consortium of Astroparticle Theory, which aims to bring together the European community of theoretical astroparticle physics and astroparticle physicists and cosmologists. And he's also very involved in outreach, as you've written 2 popular science books. And today you're going to talk about a new era in the quest of dark matter. Thanks a lot.
Thanks a lot, Kumiko. Thanks a lot to everyone. It's really a great pleasure to be back at the Institute of Astrophysics. What I would like to do today is to give an update on the status of dark matter searches. And in particular, what I would like to do is I've divided the talk in 3 parts. There's a part 0, which is sort of a preamble that has more to do with the way we talk about the dark universe in general and the narrative around the dark universe, which I think we could do better at explaining these concepts, especially when we talk to the general public, those who don't have the tools really to understand what we actually mean when we talk about the dark universe. And then I would like to tell you about the dark matter problem and what we have learned about dark matter in the past 40 years, essentially since when the dark matter paradigm was established. And then in part 2, I will go back actually to the title of this talk, which is A New Era in the Quest of Dark Matter. I would like to explain why I think we are living a new era in this field of research. So let me start with a very quick preamble. I will not spend too much time on this, but if you have questions or comments, please let me know. The first point I wanted to make is that when we talk about the history of dark matter, I think we should do better than we currently do. So if you go to an average conference on dark matter, you typically hear that dark matter was the phrase dark matter was coined in the 1930s by Zwicky, who was observing the velocity dispersion of galaxy clusters, of galaxies in galaxy clusters, and then Vera Rubin discovered flat rotation curves in the 1970s. And what you actually see, when you look closer at the history of the problem, is that already back in the early 20th century, so in 1904. Lord Kelvin actually was talking about dark matter in a very modern sense, in the sense of something that has dynamical influence on objects we can observe, but that we can't observe itself with our telescopes. And in particular, what he was doing back then, so this is 1904, before we knew that there were even other galaxies, and the universe was basically the stars in our solar system. Sorry, the stars in our galaxy. He applied what was called the kinetic theory of gases that he was himself developing to the stars in the Milky Way. And his program was basically to associate the velocity dispersion of stars with the gravitational potential of the Milky Way. And by doing that, he could connect the gravitational potential with observations. He would observe how many stars there are in the universe, were in the Milky Way, estimate their density, and compare the density with the density that he could infer from this gravitational potential. And only 2 years later, Henri Poincaré, so this is the year when Poincaré was named the director of the Académie des Sciences, he was saying, referring to the work of Lord Kelvin, he was saying, since the total number of stars is comparable to that which the telescope gives, then there is no dark matter. So he actually wrote this in French first, matière noire, and then translated in the English version to dark matter, or at least there is not so much as there is of shining matter. So I cannot really make justice to the history of dark matter, but for those of you who are interested, we recently worked with Dan Hooper, who wrote this review which is called The History of Dark Matter on Review of Modern Physics, and you can find it on the archive. And we're working now with a professor in the history of science, Jeroen van Dongen at the University of Amsterdam, and with Jaco de Zwart, a joint PhD student between us, astroparticle physics, and history of science. And he has already published a very interesting article on nature astronomy, and more will be published soon. So bottom line of this, I think if you have an interest in the history of dark matter, the history is very, very rich, and I think we can make more justice to the pioneers in this field by telling a more accurate story of how we came to accept these unseen components of the universe. The other small point I wanted to make, would probably be completely obvious to these people, to the people in this room, but let me still insist on one particular aspect, which is the following. So, as you know, in 2019, half of the Nobel Prize in Physics was given to Jim Peebles, and if you look at the motivation for his prize, you will see that he came up with essentially gave a very important contribution to the standard cosmological model. And the results of all this effort showed us a universe in which just 5% of its content is known, the matter which constitutes stars, planets, and trees, and the rest, the 95%, is unknown, dark matter and dark energy. This is a mystery and a challenge to modern physics. And this is the standard narrative that we use when we talk about the dark universe. And what we typically say is we have many pieces of evidence, of observational evidence that range from the scale of galaxies, rotation curves of galaxies, even actually velocity dispersion of dwarf galaxies, even subgalactic scales, all the way to galaxy clusters, and all the way to cosmological scales, the cosmic microwave background. And then if we piece together things like type 1a supernovae or baryonic acoustic oscillations, then we have this description of the universe, which, as we just said, is basically 95% dark and only 5% atoms. The thing is, though, and this is where we get to a point which is easily understandable by people in this particular audience, but very difficult to explain if we use this narrative when we do outreach, when we talk to the general public. This statement is valid now in this particular moment in the history of the universe, and only on particular scales. So if we look at the universe on very large scales. And if you look at the universe on very different scales, on very small scales, for example, in the local universe, like on scales comparable with the solar system, you'll see that basically everything is made of atoms, and there's very, very small traces of anything else. If you look at a 20 kiloparsec sphere around the Milky Way, 72% of the universe is made of dark matter, 28% is made of atoms, and it's only when you go on very, very large scales, when the universe is essentially homogeneous and isotropic to a good approximation, that you see this 95%. Even more importantly, and this is where it gets very confusing when you talk to when you talk about 95% of the universe being dark, is that if you look at the universe in the past, at BBN, the universe was 0% dark. The universe was completely known at BBN, for example. It was photons and neutrinos, essentially. If you look at CMB, well, so the relativistic species will have will be diluted with a to the fourth, so photons and neutrinos, and then you would have atoms and dark matter, so matter domination starting around that epoch. And then if you look today, you get 95%. So you go from 0% dark to 63% dark to 95% dark, and then if you look forward in the future, it would be 100% dark. It would be essentially dark energy will contribute to the energy density. And that's very difficult to explain to someone why the universe went from completely known after the Big Bang to completely unknown in 20 or 50 gigayears, whatever will be that we get to the point of 100% being a good approximation of dark matter. Dark energy is very difficult. So, what I always try and do is to always discuss the cosmological evolution of the various species in the universe. And again, this is, will be obvious to everyone in this room, but I think this is a more effective way of discussing, how the universe evolves, talking about expansion of the universe, how the different species evolve, matter getting diluted, and then this contribution that may or may not be connected to the energy of the vacuum space. A narrative which works very well is that of the numerical simulations of the universe, and this is where I conclude this small preamble. And this is something which is, of course, very familiar to the people in the audience, in particular at the Institute of Astrophysics. Now we have numerical simulations that are such that if you put in the ingredients of the standard cosmological model, the right amount of dark matter, the right amount of dark energy, and if you describe in a suitable manner the baryonic physics, in particular the physics that happens sub-grid in your numerical simulations, you get a universe which really looks like the universe we observe. And this is not just by looking at things, just by looking at the output of this numerical simulation, but if you really look at the statistical properties of the universe, the type of galaxies you form and things like that, really get a convincing argument that we have a model for cosmology that really provides a very good approximation of reality. However, we are accepting, and here I move on onto part one. What have we learned about the nature of dark matter in the past 40 years, essentially? We are relying on dark matter and dark energy to form the structures in the universe. And if you remember, what was the relative proportion of dark matter, dark energy, and baryons at CMB, so when structures started to form, matter radiation equality, then you see that you really need to understand what dark matter is if you want to have a reasonable and self-consistent explanation of where structures in the universe come from. Now, what do we know about dark matter? This can be, you can look at this in many different ways. This is one example of trying to collect all this information in a way which is easily, hopefully accessible. So a typical problem for people working in astroparticle physics is that theoretical physicists would come up with an explanation for dark matter, a natural explanation for dark matter. And then you have to provide all this kind of constraints that this particle would have to fulfill in order to be considered a dark matter candidate. And the way this is organized is in a sort of a 10-point test that any particle has to fulfill in order to be considered a dark matter candidate, a viable dark matter candidate. First and foremost, we have a very stringent constraint on the abundance of dark matter in the universe. From CMB, we can measure the abundance, the average abundance of dark matter in the universe with a precision of the order of a percent. We know that dark matter must be cold, and cold has a very specific meaning in this context. It must be non-relativistic at the epoch of structure formation, and this translates into a constraint on the free streaming lengths of dark matter particles. It has to be neutral, no electric charge, no color, nothing that would couple these particles very strongly with particles of the standard model. It has to be consistent with Big Bang nucleosynthesis. It has to be consistent with stars. It's crazy how difficult it is to conjecture the existence of a new particle that doesn't mess up with something in the universe. The structures of stars, the Big Bang nucleosynthesis, free streaming length, and so on. These are surprisingly stringent constraints. And then there are 5 more points that we'll not discuss in detail unless you have questions. But basically, you can set pretty stringent constraints on the self-interaction cross-section of dark matter. So dark matter is effectively collisionless. You can set constraints on the couplings of dark matter with the standard model, in particular with spin-independent and spin-dependent cross-section with nucleons as a function of mass. And then there are constraints that come from the fact that if these particles self-annihilate, they would produce a lot of radiation like gamma rays, neutrinos, synchrotron emission that we haven't observed. So you can use those observations to constrain the self-interaction cross-section. And then there is a 10th point, which is more like a philosophy of physics or philosophy of science point rather than an actual technical physics point, which is that if you want a new particle to be an explanation for the dark matter, there should be at least in principle like a thought experiment that you can perform, even if it's like 100 years from now when suitable technology will become available. But you need to have an idea about how to test this theory. Otherwise, if your solution is something that only interacts gravitationally with the standard model of particle physics, then we have performed the observations we could perform, which are the ones that lead us to the evidence for dark matter. Now, if you put together all these constraints, you can readily rule out all the particles of the standard model. There's no single particle in the standard model that can pass all these different points. And this is a dream scenario for people doing model building in particle physics, because you can just go crazy, right? You can postulate the existence of a dark matter candidate and then try to imagine experiments to test your hypothesis. Now, we've tried in this review article to kind of collect the information that we have about dark matter, possible solutions that have been proposed for dark matter. I will not go through the details of everything, because again it would be too long and quite boring. But let me go through the 6 major blobs, the big ones, very quickly. The first one is that of light bosons. And one of the main examples that I'm sure many of you will have heard about is that of the QCD axions. For completely different reasons, people were studying what happens when you try to solve the so-called strong CP problem in quantum chromodynamics. And they postulated the existence of a new particle, the QCD axion. This is back in the 70s, and people realized that this particle could explain the dark matter. It could pass all the points in this test. And these days people talk a lot about axions, about axion-like particles, and about fuzzy dark matter that belongs to the same category. Another possibility is that dark matter has something to do with the neutrino sector in particle physics. Now we know that standard model neutrinos are part of the dark matter, but they cannot be all of the dark matter. It is still possible though that sterile neutrinos could act as dark matter candidates. There's a lot of effort in trying to constrain that possibility. Then there is, maybe the main idea that people have focused on for the past 40 years is that the dark matter has something to do with the weak scale in particle physics. And there's a lot of effort that has gone in the search for supersymmetric particles and other types of particles at the TeV scale, let's say, in big colliders, for example. So this is the category that is broadly known as WIMPs, weakly interacting massive particles, that again have attracted most of the attention, I would say, of the community for the past 40 years. And then there is the possibility that is some other particles. We had to clump in a way together any other possibilities. So you may have heard about things like WIMP-zillas or self-interacting or superfluid dark matter that would fall in this broad category of still an elementary particle essentially composing the dark matter. Last 2 points I wanted to mention is that it is in principle possible that dark matter is made of macroscopic objects, and in particular, there's a revival of interest in models where dark matter is made of primordial black holes, and there's been a lot of discussion about the possible connection between the dark matter and the first events that were observed by LIGO. If you're interested, we can talk about that. This connection doesn't seem to be very, very strong. Doesn't seem to hold. There are many constraints on that possibility, but there's been a lot of discussion about this possibility here. And then there is this possibility, which is still a logical possibility, which dark matter could be the manifestation of of modified gravity, essentially. And there are many people working. Well, I don't think it's true that there are many people, but there's a community of people who are exploring the possibility of solving the dark matter problem by a suitable modification of the laws of gravity. Now, just very quickly, before I move on to more technical aspects, what is the, I've shown this mind map of possible solutions to the dark matter problem. I wanted to show at least one parameter space, physical parameter space, to describe, the range of possibilities that we're discussing here. If you plot the various candidates and you organize them by the mass of the dark matter candidate, you see that this plot ranges from 10 to the minus 22 electron volts for candidates like fuzzy dark matter, all the way to 10 or 100 solar masses, which are, in these units, in electron volts, that's, 10 to the 70 or so. And I don't think there are many fields of research in which anyone would plot, would show a plot with an uncertainty over 90 orders of magnitude, right? Yeah, but this is, I think, this tells how uncertain the field currently is. These columns here, the width of this column is basically given by the range of masses that are considered for a particular candidate. The height of this column is roughly proportional to the number of papers that have been published on that particular candidate. And you see that there are WIMPs are by far the candidates have been most explored in the literature, and axions, sterile neutrinos, fuzzy dark matter maybe are.
Do you mean axions as dark matter or
axions as dark matter, specifically as dark matter?
There's a lot of publication about.
Yeah, no, this is specifically in the context of dark matter. Yeah, and I've also excluded from WIMPs all theories about all papers on supersymmetry that were not directly considering the fact that dark matter would be the supersymmetry particles had to do with dark matter. Now, the main paradigm that people have focused on for the past 40 years, since the 80s, essentially the early 80s, is the paradigm of WIMPs. I'm sure you have heard about this candidate. The idea is extremely simple, and if you're a particle physicist, this seems maybe one of the most natural ways to proceed if you want to explain how dark matter is produced in the early universe. The idea is basically that you put your dark matter particle in thermal, kinetic equilibrium with other particles in the early universe, and then you ask the question, what are the couplings that this dark matter particle has to have? So you see this is dark matter annihilating to standard model particles, and this process is kept in equilibrium in the early universe. At some point, you want these dark matter particles, the density of these dark matter particles to freeze out, so to decouple from anything else in the universe, and you want basically your clock for decoupling these particles from the rest of the universe is provided by the annihilation cross-section, so that sets the strength of this interaction. If you tune this cross-section, if you make it very high, these particles will remain in equilibrium for a very long time in the early universe. Their density will be Boltzmann suppressed, and their Bragg density will be very small. If your annihilation cross-section is very small, they will decouple very early in the universe. There will be no Boltzmann suppression. The Bragg density will be very high. And so you can play this game and ask. You can write down the Boltzmann equation that regulates this problem. Not sure you can see this very well from there, but it's a simple equation that regulates basically the evolution of the density with time in presence of an expanding universe. So this H factor encodes the expansion rate of the universe. And then on the right, you have sigma v, which is the annihilation cross-section, and the departure of the physical density of these particles from the equilibrium density they would have. You can solve this equation and calculate, at least in an approximate way, what would be the relic density, so the abundance of dark matter in the universe. And then you see that this is a number. It is 3 times 10 to the minus 27 centimeters cubed seconds minus 1 divided by the annihilation cross-section. If you plug in a weak scale cross-section in this expression, you get an omega h square of 0.1. And at the end of the 70s, 90s, beginning of the 80s, this was thought to be a beautiful coincidence, and was referred to the WIMP miracle. The fact that by postulating the existence of new particles at the weak scale in particle physics, which is where particle physicists were working really to postulate the existence of new scale for completely different reasons, then you would have a problem for the dark matter in the universe. And many a lot of effort has gone in the search into the search for these particles. And if I had given this talk like 10 years ago, I would have told you a lot about the searches for WIMPs at accelerators, the searches of WIMPs with astronomical observations, the search for the so-called indirect search, the search for the annihilation or decay products of dark matter particles, and so-called direct searches, these experiments that you place deep underground and search for dark matter particles going through them, basically, and trying to catch the signal, the very rare interactions where dark matter interacts with these particles. Now, none of these experiments, so what we've done so far, basically, was to build exclusion plots. We know a lot about what dark matter is not, but we don't know what dark matter is. And the way this is presented, depending on the specific field you work in, so if you have if you look at the proceedings of particle physics conferences, you will see a lot of diagrams showing you lower limits on the mass of supersymmetric particles. So you know that if supersymmetric particles were lower than typically the TeV scale, we would have seen them at the Large Hadron Collider. Because we didn't, we only observed processes compatible with the standard model of particle physics. We can rule out the entire portion of the parameter space which lies below the scale of the TeV. Similarly, in the case of annihilation and decay of dark matter, the searches, for instance, of gamma rays from the galactic center or gamma rays from dwarf galaxies, they've allowed us to set an upper limit on the annihilation cross-section as a function of mass. Again, the idea is that if the annihilation cross-section was higher than a certain value, we would have seen gamma rays from the galactic center. We didn't. I'm happy to discuss that. For everything that I'm saying now, there are caveats and conferences organized about it. So I'm just trying to give the big picture. If you have specific questions, please feel free to ask. And similarly, in the case of direct detection, if you plot the spin-independent scattering cross-section of WIMPs of nuclei as a function of mass, again, current experiments have set an upper limit on that parameter, on that cross-section, because if the cross-section was above that particular value, we would have seen events in our detectors, and we didn't. Okay, so I think it's fair to say that no WIMPs, and in fact no other dark matter particle has been observed in any experiment despite many efforts. There are intriguing hints here and there, and if you're interested, I'm happy to discuss them. So, but there are also kind of sociological aspects. 10 years ago, 20 years ago, people would use dark matter particle and WIMP and neutralino almost as synonyms, and of course this wasn't the case back then. But if you ask me, what is are WIMPs ruled out by current experiments? My simple question to this question, the simple answer to this question is no. Okay, and so there's a one-line argument that hopefully conveys the main message, which is the fact that absence of evidence in general is very different from evidence of absence, and what we currently have is absence of evidence for these particles. From a more technical point of view, I think it is fair to say that the connection between the dark matter problem and the so-called naturalness problem in particle physics, which boils down to the fact, why is the weak scale in particle physics so different from the scale of gravity, basically, or from the Planck scale in particle physics. All the arguments have been put forward to explain that particular, those kind of problems. They are in trouble, I think, now. However, and there's a nice paper by a particle physicist, a theorist whose name is Giudice, who elaborates basically on the concept of naturalness after we've run in particular the LHC at high central mass energy, a 13 TeV central mass energy. But there are also some more technical points that I wanted to make for the experts in the room. The first one is that non-fine-tuned supersymmetric scenarios still exist, and there's an industry actually of papers that seek to find corners in the parameter space of supersymmetry where you can still have everything you were hoping to get. So basically, a natural solution to the dark matter problem without being in conflict with accelerated results. And then there is the fact that, as it often is in the history of science, the very concept of naturalness, or the very concepts that were at the basis of the so-called WIMP miracle, they themselves evolve. And I was intrigued by reading this article. I put a reference here where they elaborate precisely on on this concept of what is a natural extension of the standard model today, with respect to what natural meant when WIMPs were first proposed 40 years ago. Another quick point that I wanted to make is that the WIMP paradigm is, so to talk about WIMPs as dark matter candidates is different from talking about WIMPs as, in the context of the WIMP miracle. And what I mean with that is that, the strong interest in the WIMP problem was that you put together, so you had basically two problems that were solved with the same hypothesis. Now, the fact that this hypothesis doesn't solve one of the two problems doesn't mean that it is not a valid solution to the other problem. So WIMPs, in terms of being good dark matter candidates, they're just fine, right? Just need a particle that decouples with from the rest of the universe very early on, with a cross section at the weak scale. The fact that this, that we don't know any natural theory in which this happens, well, this could be considered a problem of particle physics, not of cosmology. And the other point I wanted to make is that in any case, there's a clear way forward for dark matter searches. And in particular, the LHC, will continue to collect data for 10, 15 years. We've only connected a few % of the total amount of data that will become available at the LHC. So for me, there's no question that we should keep searching in the products of the collisions at the LHC for dark matter particles. And for what concerns the direct detection experiments, the situation there is a bit different in the sense that these experiments are really dedicated experiments. We build them to search for WIMPs. Okay, so if WIMPs are not there, if we knew at least that WIMPs didn't exist in the universe, there would be no reason, or almost no reason, to build that kind of experiments. But the nice aspect, the nice part of it is that there's a sort of a natural limitation. This could sound like a bottomless search, basically. You improve the sensitivity of your experiment, you don't find anything. You go another order of magnitude in sensitivity, you don't find anything. The question is, when do you stop, essentially? And there's a clear answer in the case of direct detection experiments. There's something called the neutrino floor. So there's, if you increase the sensitivity now by, I think, between 1 and 2 orders of magnitude, probably closer to 2 orders of magnitude with respect to where current experiments are, you start to pick up neutrino coherent interactions. So the neutrinos, standard model neutrinos, will start to interact with xenon nuclei, and will produce a signal that would basically make further progress very difficult. Okay, so there's a natural way to go for WIMPs. And now I move to the second part of this talk, which is the last 10 minutes basically, which is why are we talking about a new era in the quest for dark matter? And the main point here is that the dark matter searches for the past 40 years have been had this basically goal, or you may even call it sort of theoretical prejudice of most of the community, that dark matter had something to do with the weak scale in particle physics. We haven't found this we haven't found these particles. Now it's fair to ask the question, what is the best way forward? You know, what kind of searches should we perform in the future, and you know, how shall we attack really the problem? And I want to give you, I will argue actually the main point is this. The first one is that we should broaden, improve, and diversify current searches. The second one is really that we should go back to the data. We should take a hard look at what astronomical and cosmological observations are telling us about the nature of dark matter. And third, we should try and exploit gravitational waves, this new portal, basically, to understand what dark matter is. And I cannot make justice to each of these 3 points. These are really, you know, 3 lines of research. But I want to mention at least one example in each of these 3 points to give you an idea of what is happening today in the field of dark matter searches. The first example I wanted to show you has to do with accelerator searches. Now, I told you how people search for new particles at the weak scale, right? So at the TeV scale, and at the Large Hadron Collider. And this is like a pictorial visualization of what happens inside the Hadron Collider. And what this video will show you is basically that you go inside the beam pipe, basically, where people write Lagrangians on the walls. And then basically you go inside really the beam pipe, and you see basically the protons with the quarks being accelerated at 13 TeV, and then being collided. At the center, there are 2 beams of protons moving in opposite directions, and they are made to collide at the center of bit detectors, like the Atlas and CMS detectors. Now, as you can imagine, searching for the products of the collisions of these proton beams is quite a daunting challenge, especially when, you know, your theory for your extension of the standard model of particle physics has many free parameters, right? You know, we have ideas about how to have the standard model, but these ideas are poorly constrained from data still. And the way this actually works in practice, and the way we've attacked the problem in the past, was basically that we had a model that in the context of particle physics means, you know, you write down a Lagrangian, which has contains basically information about the particle content of the new theory and the couplings among particles. And then you feed your model into a big piece of code that computes the phenomenology, so the type of particles, the decay times, and, you know, all the things that are relevant for the phenomenology of your model. And then it passes this on into a detector simulation that tells you how a detector, a DLHC, would respond to your particular dark matter model. And then, you know, the output of this you can directly compare with the data. But this process is very expensive. You know, if you do it, you know, carefully, it could take you, like, for one particular choices of your parameters, it could take you, like, you know, 10 minutes. And you can imagine, you know, if you have a 24-dimensional parameter space, you know, you would have to probe this with, you know, billions or, you know, tens of billions of likelihood evaluations, and this is extremely expensive and in practice unfeasible. What you can do now, and what is happening, and this is the example I wanted to show you in terms of, you know, improving or diversifying our searches, is that you can build surrogate functions, surrogate models. These are, you know, based on machine learning algorithms that allow you to go, that basically learn the mapping between the model and the data without running at each point in the parameter space the full calculation that is very computationally expensive. And by doing these kind of things, well, first of all, you realize that there are, you know, these current methods for speeding up these likelihood evaluations are extremely efficient, and you cut the computational times by, you know, 4 orders of magnitude. You went on, so this is what we were discussing with the students this morning. We went, in this particular example, we went from 400 CPU years to 2 CPU weeks that, you know, a PhD student can now run on a desktop. So this enables, you know, a much faster, much more effective way of exploring the parameter space of new theories. And for those of you who are interested, we have a collective called Dark Machines. And there's, you know, the website here. The next conference will be at CERN at the end of April, precisely to discuss the recent advances in machine learning and how they can help the search for dark matter. The second point I wanted to make has to do with astronomical and cosmological observations. And in particular, I wanted to discuss the search for substructures in the distribution of dark matter in the Milky Way. So the main problem we're after is to understand the particle. Oh, you can't see almost anything here? Is it because I didn't start the movie? Okay, now it started. So this is a numerical simulation that's probably familiar to some of you, the Via Lattea simulation. You can't see almost anything, and it's not a problem in the sense that all I wanted to convey is that if you simulate the formation of a galaxy like the Milky Way with cosmological simulations, what you end up predicting in the context of cold dark matter is that there will be many substructures in dark matter substructures in the main halo of the Milky Way. And the colder your dark matter is, the more you can extend the mass function to small values of these subhalo mass functions. So the way we understand really how matter is assembled in big structures like the Milky Way is by the merger of these small substructures in the main halo of the Milky Way. You see slowly appearing here. And the standard prediction of these cosmological simulations is that if dark matter is cold, so if the velocity dispersion is very small for these dark matter particles, then you should say many of these substructures that have remained in the halo of the dark matter, or in the halo of the Milky Way. Now, how can you search for these objects? This is an exercise that we did using Gaia data. And the specific probe that we used for the granularity of the distribution of dark matter is streams of stars, And probably you're familiar, probably even more familiar than I am with these observations. You know that if you take like a globular cluster and you throw it in the potential of the Milky Way, because of tidal interactions depending on what is the specific orbit of this globular cluster, but due to tidal interactions of the globular cluster with the gravitational potential of the Milky Way, this globular cluster can be basically tidally elongated and form these very long streams that are seen actually to wrap around our galaxy. And the specific physics problem we are after is to ask the question, can we search for these substructures, this granularity in the Milky Way, by searching for gaps or other departures from homogeneity that are induced by these substructures interacting with the stars in the stream? Okay, so my time is almost up, but let me just give you the key point that I wanted to mention. And then I can tell you more if you're interested, if you have questions. If you study the departures from inhomogeneities, or the power spectrum basically of the inhomogeneities, departure from uniform distribution of stars, as a function of the angle in the stream, what you see here, these are the data that we basically obtained by studying the distribution of stars in one particular stream, the so-called GD1 stream. And this colored region here is our best estimate of how much baryonic substructures would contribute to inhomogeneities in the distribution of stars. In other words, if baryonic substructures like giant molecular clouds, globular clusters, spiral arms of the Milky Way, the bar, and so on, were sufficient to explain the observed inhomogeneities, they should go, in principle, through the data. And there seems to be a lack of power in large angular scales. So what we did is, we took the results of a numerical simulation of cold dark matter. We put the predictions of these numerical simulations, and you see that in general, you have enough power to explain the data from dark matter subhalos in the cold dark matter paradigm. So this is just one example of what can be done, and this example is actually several groups already followed up on our measurement, let's say, of these inhomogeneities, and I'm happy to tell you more if you're interested. So Do I have 1 or 2 more minutes to finish the presentation? I just wanted to give you one example about this third point, you know, the use of gravitational waves to test dark matter. Now, I'm sure you're all familiar with the fact that you know, we have had the first direct detection of gravitational waves, and I'm sure you've heard that there were many more detections after the historical one, for which the Nobel Prize was awarded in 2017. Now, the specific observable that we're after in this case is what is the consequence of dressing black holes with dark matter. The idea here is that in whatever you do to grow black holes from small seeds, you end up predicting overdensities of dark matter around them. Now, how much dark matter you form and, you know, what is the slope of this overdensity is, you know, depends on the physical parameters of your system. But the point that I want to make is that if these dresses of dark matter exist around black holes, so instead of having naked black hole merging in vacuum, these objects are dressed with dark matter, then the presence of dark matter will affect the dynamics of the spiral. And this is, you know, shown with a little movie that was run by these 2 postdocs in Amsterdam. And what you see is basically that because of dynamical friction, largely because of dynamical friction, the orbits of these 2 black holes is severely affected. In fact, what's happening is that the energy of the binary is being transferred to the dark matter distribution. So as you can see, there's very little dark matter around these 2 systems, and you know, due to dynamical friction, the separation between these 2 objects has decreased, and the orbit is becoming also more circular. So we're hoping basically to use the signature of these of dark matter dresses on the waveform of merging black holes, in particular in the case of extreme mass ratio in spirals, hoping that this will tell us something about the distribution of dark matter and possibly about the particle nature of dark matter. We're still at the beginning of this program. There's still, you know, so much to understand the interplay with baryons, accretion disks, you know, how you can distinguish in the first place you find d-phased waveforms, and once you found them, how can you do kind of model selection? Can you tell the d-phasing induced by an accretion disk from the d-phasing induced by a dark matter dress, or from that induced by modified gravity? So this is a program that is, you know, has just started and probably will last for many years. And let me conclude here. I had some comments on primordial black holes, but I don't have time to go through them. Let me just come to my conclusions. I really think, and I hope I conveyed this message today, this is a moment of profound transformation for dark matter studies. In view of the absence of evidence, which is different from evidence of absence, of the most popular candidates. The current searches, like Large Hadron Collider, indirect detection and direct detection, may still reserve surprises. So I'm not arguing that, you know, we should stop building direct detection experiments. At the same time, however, it has become quite urgent to diversify our searches, to exploit astronomical observations, really to go back and ask, you know, what are the data telling us about the nature of dark matter, astronomical and cosmological observations, and then to exploit the new opportunities offered by gravitational waves. And the more in general message especially for the young people in the room, you know, we're not doing finance here. You know, crisis, you know, you often hear that there is a crisis in cosmology. Crisis is not, you know, a negative term for science, especially for young people. It means that there is room for new opportunities for new ideas and new discoveries. And I'll stop here. Thank you.
Thank you very much, Gianfranco. Yes. Okay.
Thank you. You miss 2 fundamental points in the characterization or constraining of dark matter. And as you said, in the 40s, or in the 80s mainly, abundance of dark matter, of course, mean density, but from the late 80s and the 90s till now, it was completely acknowledged that the second fundamental constraint is the phase-space density, mainly mean phase-space density, namely the velocities of the particles. This is Dalcanton-Hogan, Lindenbell, De Vegan-Sanchez, and many others people in Europe. And doing that, you constrain and almost with the very well Gaia and most early Sherry Gilmore and team exclude theoretically the excessively massive particles, namely Giga electron volts, TeV electron volt, etc., which is the reason why all the dedicated experiments have not found positively the dark matter particle. Conclusion: what is presented here as new era is in fact the acknowledgement that all that failed, and you can, I mean communities, could continue to say very big WIMPs still there, WIMPs, massive particles still there, and all the spectrum is still there. This will not give discovery. This is not a strategy of discovery, this is a strategy of constraints. And that is the reason why, during all these 40 years, dark matter is one of the, perhaps the only subject in which cosmology have not made discoveries, and the reason why dark matter have not had a Nobel Prize, because the last Nobel Prize is
so we got the point. Okay, maybe we can...
Gianfranco, first I would like to thank you for this talk. It's the best talk on dark matter I've heard in my life.
Okay, thank you.
And I remember times when there were no talks about dark matter. Now, I have a problem with with these conclusions, because of course the absence of evidence is not evidence of absence, but what is evidence of absence? In other words, you are going to look for WIMPs, for axions. Can you predict when you will say, okay, we found nothing, and now we decide there is no dark matter in form of particles, for example? Or you can go to infinity and have then problem with finances, of course, because you will need a more powerful accelerator. So do you see a way of saying, okay, there is no dark matter?
Yeah.
Because if not, is it science?
Yeah, no, I agree. And you know, this effort that we're trying to make, you know, precisely goes in the direction. I completely, feel your I don't want to say irritation, but certainly, the fact that you would like to get an answer and you don't want to, tweak your theories, and you make them consistent with any type of observation you perform. Now, what I can say is, I don't have, answers for the whole community, for all particles and for all candidates. What I can say is that there was a clear case for these natural WIMPs, the WIMPs that would solve at the same time the problems in particle physics and the problems in cosmology. I thought this was, super exciting connection, and it was worth, searching for these particles. Just as I like, the connection with QCD axions, very specific predictions about the masses and the couplings, and I think we should get there and to probe them. Now, of course, and this has always happened in the history of science, whenever there was a measurement that contradicted predictions, scientists were very quick at adjusting their predictions, right? To make them, around the corner or around the next corner. And this point that I was making, we should diversify our approach, was precisely in the sense of, let's not focus on our theoretical prejudice or what things, what we would like dark matter to be, but go back and perform the observations that can tell us whether dark matter is in the form of a light KV relic or a very heavy cold relic. And the observations that I presented here, they can give us very broad informations whether dark matter is made of WIMPs, of axions, or other things. You can map basically these phenomenological observational constraints into your favorite dark matter model. But what you say is precisely the kind of approach that I'm kind of pushing, which is less driven by theoretical prejudice and more driven by the data.
Thanks a lot, Gianfranco. It was a great talk, and I have a million questions we can discuss later. I guess I'll ask you one. So I think I remember, and I haven't followed this closely lately, but I think I remember there were like proposals to beat the neutrino floor in some ways. And
yeah, there are some, various people are kind of pushing in that direction. So I'll give you one example, one obvious example of how to beat the neutrino floor would be to have a directional detector, right? If you know where your particles are coming from, you know if these are neutrinos from the sun or whether it's something that modulates with the motion of the Earth around the sun. The question though is, what is the motivation for doing that, right? At that point you would have to scale, especially for this, unless you have a cheap way of doing this, which doesn't exist yet. The idea to build like a kilometer cube detector to find basically unless there is a theoretical or a fundamental interest in understanding the physics of neutrinos. So if there is like a guaranteed physics that you can do, you say I want to find the diffuse supernova background with my detector, and this detector will search for the dark matter and will give me information about that. Then fine. Otherwise, it's very hard to justify the investment to go beyond there because there's no guaranteed discovery below the floor.
My related question is whether in direct detection you have a cross section that you say, this is like an interesting thing that we would like to reach.
No, not inside. So maybe there is some kind of fundamental theoretical bottom of that plot. But this would be many, many orders of magnitude below. Even in simple realizations of supersymmetry, you have particles that could have cross sections which are very, very small.
Thanks for the very interesting talk, Gianfranco. Always nice to say a bit about Kelvin at the start. I didn't know that particular story, obviously. So I guess you didn't actually say personally what's your confidence that dark matter is a WIMP between 0 and 100. And the second question was, could you maybe say a bit about, we heard at a few seminars about the possibility there might be a resolution from tabletop physics experiments. So maybe you want to say something about that, like the
tabletop experience about?
Tabletop physics experiments, like doing experiments in the lab on the fine structure constant, things like that.
Right. So yeah, I prefer not to give percentages. I've personally worked in the field of WIMPs. And so like 10 years ago, I wrote an article that was called The Moment of Truth for WIMP Dark Matter. And what I said is basically what is happening now, looking back at what was the content of the article, which is that we can't, because the theory space is so complex, it's very hard to rule it out completely and to say, WIMPs do not exist. On the other hand, we ruled out so much parameter space that it's very difficult to remain excited about that possibility, especially when you break the connection with the particle physics problems that motivated the WIMP paradigm in the first place. So I'm not giving you a number, but I can certainly tell you that the percentage is way lower than it was 10 years ago. Okay. About the tabletop experiments, there are different ways of searching for new physics. I don't know exactly what you're referring to, but there are some ways of searching for changes in fine structure constant or other constants of nature. I don't find them particularly well motivated from a theoretical point of view. But if one of these experiments turns out to produce some interesting results, of course, it's worth following up.
Hi, Gianfranco. Thanks for the interesting talk. I have two questions. So let's say the first one is, I found very exciting this, one of the last things you mentioned about the gravitational waves and the measure of the black holes. Can you give us just an idea, a glimpse, why you think it will be possible not just to understand the distribution of dark matter around the black holes, but also the nature of the field?
Yeah.
And the second is just, if you have like also, you can give also a comment about, because you completely, because of lack of time, you didn't mention primordial black holes and modified gravity. You don't give any hope to these ideas, or it's just that they are the last one and they didn't fit in the time?
I'll just give you one quick idea about how the, by probing the distribution of dark matter can tell us something about the nature of dark matter. Suppose you start from so I'll give you the short version, and then I'm happy to tell you more. Suppose that you have the density as a function of the radius of this dark matter around black holes. Now, if this is, let's say the ISCO, so around the innermost stable circular orbit around the black hole, so like, what is it? Help me, 6 times the gravitational radius? For a Schwarzschild black hole, right? Then you basically have dark matter that would be distributed like a power law in the outside this region, which then dark matter would essentially fall in, and this, well, depending on the formation scenario of the black hole, you can reach, in principle, because you're going to very small density, and this is a power law, you can reach very, very high densities here. If dark matter is a WIMP, then there will be a maximum density that you can, above which basically all the dark matter will be completely annihilated away, right? Because the annihilation, you can actually, in dimensional arguments, you can write this maximum density as, the mass of the particle divided by the cross section times the time since formation of this object, right? So if you see that there is a lot of dark matter right here, you know that this cannot be annihilating dark matter, because there's no way of keeping it there with these very high densities for long enough. Okay, so this is a possibility. Another hint is, if you see something that doesn't want to cluster on small scales, so this is what happens for cold dark matter. But if this is a fuzzy dark matter, an ultralight boson, this will not be a power law. There will be field configurations like orbitals, like electron orbitals around the hydrogen nucleus, basically, and this would have a completely different shape and a completely different evolution of the waveform as you move in. So depending on the nature of dark matter, you can hope to find a different signature in the waveform, but this is largely unexplored. This is something we're basically starting now, and it's worth looking in more detail. Quick answer, and then we can discuss more about primordial black holes and modified gravity. So primordial black holes is it was very intriguing, the fact that first of all I think we all understand that primordial black holes have been proposed even before WIMPs as dark matter candidates. Okay. Now, people there was a revival in interest in primordial black holes because LIGO found these 40 solar mass objects merging with each other, which was essentially the only mass window where you didn't have very stringent constraints on the amount of these objects in the universe. Now, since then, many people have looked into that, and they've essentially closed that window. It is conceptually possible that, because there are many systematic uncertainties in all current constraints, it is in principle possible that you can really push the parameters of one constraint in one direction and all the systematic uncertainties in another direction and make again that particular window available, but that doesn't seem very promising, honestly. There is one window which is still open right above the evaporation scale of black holes, of primordial black holes. So these would be objects with a mass of an asteroid, essentially, and really microscopic sizes. And that's still a possibility. But the parameter space really look very, very constrained. And the other thing is that even if there is a one window which is open, that doesn't guarantee you that these objects can explain all of the dark matter unless their mass function is really monochromatic, to fit in that window and not to be affected by constraints on the tails of the distribution on one side or the other. So it is still theoretically possible. That doesn't seem particularly promising. Modified gravity is still a theoretical possibility. I still have to see, I know that, also people like Luc has worked on this possibility. My impression is that, so most people when they talk about modified gravity, they think about kind of Mond-like phenomenology. So I think it's fair to say that Mond works surprisingly well on the scale of galaxies. There are some regularities that you observe there that, at least you wouldn't a priori predict if you didn't know that they exist. Now we try to explain those regularities using the things we know, and in particular numerical simulations. And looking at, just to mention one thing, you probably have seen this universal acceleration relation of Megor and others, where basically they plot the observed acceleration of of stars in galaxies as a function of the acceleration provided by baryons, the gravitational potential provided by baryons. And there seems to be a very tight correlation between these two quantities, which deviates from a Newtonian behavior, and it deviates more or less at the same scale in terms of acceleration in all systems. Now, if you look at this, you immediately say, oh wow, this seems to be a very tight correlation. Maybe there is something interesting. However, the first thing we did when we saw the paper was to plot the relationship that we obtained in our, we were analyzing some numerical simulations from the EGO set of simulations, and in particular the Apostle simulations, and we plotted the quantity for the stars and the total dark matter distribution in those galaxies, and basically it was following the same relationship. And in a way, it's normal, right? There's a connection between how much dark matter there is in a system and how many baryons you have in the system. I think the interesting point is that relationship is very tight, right? Because there is a correlation. It's kind of obvious. The interesting thing is that it's very tight. And the other interesting thing is that if like people like me think, this is just due to standard dark matter, there's a clear prediction that you can make, which is that if you observe these systems at higher redshift, this relationship, if it is due to dark matter, would evolve. If it's due to modified gravity, it shouldn't, because it's just a gravitational potential effect, basically, that doesn't evolve with redshift. So also in that case, I think observations will tell us in which direction we should go.
Okay, thank you very much. So unless there is a pressing question, we will thank you.
Thank you.